Good morning, everyone. So welcome to my YouTube channel, Math Saptram. So today we are going to see 13 lecture on Riemann integration. So let us start today's session now. So today we are going to prove two important results. One is that monotone functions on closed interval AB is Riemann integral, and another one is you take any continuous function on closed interval AB, that is also Riemann integrable. Okay. So let's see. So theorem 1 we are saying it. What is theorem 1? Theorem 1 is let F closed interval AB to R be a monotone function. Then F is Riemann integrable for closed interval AB. It means, what does it mean? It means F belongs to R AB. Okay. The meaning of this, F is Riemann integrable R means that F belongs to RAB set. RAB means collection of all the Riemann integral function over closed interval AB. So let's prove it. It is simple. So we are taking, because F is monotone function means either F is monotonically increasing or monotonically increasing. F is monotone on closed interval AB. This implies either F is monotonically increasing or F is monotonically decreasing. Okay. So we will prove only for monotonically increasing. Same proof can be repeated for monotonically decreasing also. So without loss of generality, we assume that F closed interval AB to R is monotonically decreasing. Same proof can be repeated for monotonically decreasing as well. Okay. So we are doing for monotonically increasing only. Okay. Okay. Let epsilon greater than 0. Okay. And P is equal to AX naught, X1, X2, Xn is equal to B, be a partition of closed interval AB. Okay. Okay. Closed interval AB. Okay. And this partition, and we are taking its norm, and let P be a partition of it with norm of P less than epsilon upon FB minus FA plus 1. Okay. We are taking this one. Okay. I am taking my delta epsilon upon FB minus FK plus 1. Okay. Okay. Now UPF minus LPF is equal to summation I goes to 1 to n capital Mi minus small mi delta xi. But f is monotonically increasing. Monotonically increasing, then what will be capital Mi? Because f is monotonically increasing, capital Mi will be nothing but f xi. And what will be small mi? This will be f xi minus 1. Because it is monotonically increasing function. Okay. So once you have a greater value of f, you have corresponding value f greater than fxi minus 1. So infimum will attain xi minus 1 and supremum will attain xi minus xi. Okay. Because function is monotonically increasing. Now what is this? The norm of partition is less than delta, less than epsilon upon fb minus fa. So delta x is strictly less than epsilon upon fb minus fa plus 1. So it means this is less than I goes to 1 to n fxi minus fxi minus 1 epsilon upon fb minus fa. Okay. Plus 1. Because this is constant, I can take it outside. So if you take it outside, fb minus fa plus 1, and this is summation I goes to 1 to n fxi minus fxi minus 1. Okay. So tell me, after solving it, what you will get. This will be, after solving it, it will be, what will be this? This will be fxn minus fx naught. It will be this one. Okay. And you write this one, epsilon upon fb minus fa plus 1. But xn is b and x naught is a. So what you got? You got epsilon upon fb minus fa plus 1. This is fb minus fa. So because f is monotonically increasing, fa minus fa can be equal also. In that case, this will be 0 whole quantity. If fb minus fa are not equal, it will be strictly less than epsilon. Okay, strictly less than epsilon if fb minus fa not equal, because denominator is greater. Okay, and what about if fb minus fa this will be 0? Then again it will be less than epsilon. So it means you have UPF minus LPF is less than epsilon for any partition P of closed interval AB with norm of P less than epsilon upon FB minus FP plus 1. Okay. And this quantity is greater than 0. So it is delta for me. So what does it mean? It means that, what does it mean? It means F is RAB by theorem by theorem 1 of Riemann integration lecture 8. Riemann integration lecture 8. Okay. So hence F is Riemann integrable over closed interval AB. So we are done. Okay. Now, what is the use of this? For example, Fn okay. So, for example, you take any monotonically increasing function. For example, you take Fn x is equal to x to the power n on closed interval 0, 1. Okay. Then Fn is Riemann integrable over closed interval 0, 1 for any n belongs to natural number union 0. Okay. Solution was so Fn x is equal to x to the power n. When you take n is equal to 0, it will be one constant function. Constant functions are monotonically increasing. Or you take any natural number, then is monotonically increasing over closed interval 1. Okay. By theorem 1, Fn belongs to RA01 or any n belongs to natural number union 0. Okay. So Fn is Riemann integrable. Okay. We are done. Now next result is that theorem let F closed interval AB to R be a continuous function be a continuous function, then F belongs to RAB. Proof. In previous theorem 1, you know that every monotonically increasing function is bounded. Okay. In this theorem, we have not written this, but every monotonically increasing function is bounded. Okay. So we are writing here, note that, note every monotonically increasing function is bounded on closed interval AB. Okay. You take any monotonically increasing function on closed interval that is bounded. Okay. It is obvious because minimum value is FA or maximum value is FB because function is monotonically. So F is bounded in between FA and FB. Okay. Okay. Now, first of all, we know that every continuous function on a closed and bounded interval. It means compact set. Compact set, closed interval AB is continuous. Is bounded. Every continuous function on a closed and bounded interval, it means compact set is bounded. Okay. So F is bounded. Now, since F closed interval AB to R is continuous, so this implies F is uniformly continuous on closed interval AB. We know that every continuous function on a closed and bounded interval is uniformly continuous. So it is uniformly continuous. Okay. Now, let epsilon greater than 0. Okay. Since B minus A is greater than 0 and epsilon greater than 0, by R की median property of real numbers we have 1 upon n naught B minus A less than epsilon for some natural number belongs to, okay, for some natural number n naught. Okay. Okay. Now, next, 1 upon n naught is greater than 0 and F closed interval AB to R is uniformly continuous. There exists delta greater than 0 such that F x minus Fy less than 1 upon n naught for all xy belongs to closed interval AB with their distance less than delta. Okay. Take for any partition P of any partition P is equal to AX0, X1 of closed interval AB with norm of P less than delta. We have what we have ULPF minus LPF is equal to summation I goes to 1 to N FXI, sorry, F MI minus small mi delta xi. Okay. Okay. So this is because mi. What is so now note one thing, since mi is supremum over fx, x belongs to xi minus 1 to xi. Okay. So what does it mean? F is continuous function. Continuous function is always attain its supremum and infimum. Okay. So there exists, implies there exists, since f is continuous on xi minus 1 to xi, okay, on this interval. Okay. So there exists yi belongs to xi minus 1 to xi such that capital Mi is equal to Fyi. Similarly, because infimum is also attained, there exists Zi belongs to xi minus 1 to xi such that small mi. So we'll write it here, okay, in a proper language. Okay. So no need to write here. It means I will say, if I will write in a proper way here, in next line, it will be more, it will be good then. Okay. Or we will use another technique here. So let's say this is equation number 1. We know that mi by lemma in Riemann integration. We will doing Riemann integration lecture 12. Okay, we have mi minus mi is equal to supremum of f z1 minus f z2. z1 z2 belongs to xi minus 1 to xi. Okay, but the norm of partition, since norm of delta xi is less than delta, since this is less than delta, so f is uniformly continuous, so this is less than supremum delta. This quantity is less than what is less than 1 upon n naught. Okay, because this is less than norm of this is less than delta. And what is this? This is xi minus 1. Okay, so I am writing it in a proper way. Since xi minus 1 is equal to delta xi, and that is less than delta, or I goes to 1 to up to n. Okay. Okay. So this quantity, you take any z1, z2, their distance also will be less than delta because they are lying in this interval. So this is less than 1 upon n naught for all z1, z2 belongs to xi minus 1 to xi. Okay. And what is this? Okay. So this is 1 upon n naught. Okay. So this implies mi minus mi is less than 1 upon n naught, or I goes to 1 to n. Now from 1 we have what we have? UPF minus LPF is equal to summation I goes to 1 to n capital Mi minus small mi delta xi. But this is less than 1 upon n naught. So this means so I can take 1 upon n naught outside. Summation I goes to 1 to n delta xi. Now what is this? This is nothing but b minus a. This is nothing but b minus a. So 1 upon n naught. This is b minus a. But this is less than epsilon. Because 1 upon n naught b minus a is less than epsilon. So this implies given any epsilon greater than 0, there exists delta greater than 0 such that for any partition P of closed interval AB with norm of P less than delta, we have we have UPF minus LPF less than epsilon. So what does it mean? It means F is Riemann integrable by theorem 1, Riemann integration, lecture 8. Hence, every continuous function f close interval a b to r is Riemann integrable. Okay. So example, since sin x, cos x, cosine square x, cos square x, okay, etc. are continuous on AB. So this implies these functions are Riemann integrable over closed interval AB. Okay. Now next example. For any n belongs to natural number union 0, x to the power n function is continuous on AB. Okay. This implies x to the power n is Riemann integrable over AB. Okay. In particular, any polynomial Px is equal to a naught x to the power n plus a1 x to the power n minus 1 plus a2 x to the power n minus 2 plus a n minus 1 x plus a n is Riemann integrable over closed interval AB. Why this is happening? Because a and x to the power n, you take any natural number, these functions are Riemann integrable. You multiply any scalar with them, they are also Riemann integrable. Then add scalar multiplication in Riemann integrable functions. If you multiply with any scalar in Riemann integrable function, the resultant function is also Riemann integrable. You take any finite sum of Riemann integral function. It means you take any two Riemann integral function, their sum is also Riemann integral. Therefore, polynomial is Riemann integral because x to the power n is Riemann integral, x to the power n minus 1 is Riemann integral. We are multiplying with them a naught, a1 respectively, and we are adding them. Okay, so that is why it is Riemann integral. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. Thank you very much for today's lecture. We will see you next lecture.